Let's continue our party with complex numbers. We're going to look at some properties of complex conjugates right now. So if we have the conjugate of a complex number z, and we take the conjugate of that, we get the original complex number. If we add two complex numbers together and take the conjugate, we could really just take the conjugate of each one separately and add them. And similarly, the rest of these. One that's interesting is if we take a number and multiply by its conjugate, what we actually just need to do is take the magnitude of the complex number and square it. So these are fairly straightforward to show that they're true. For instance, this one here, if we have a plus bi, a1 plus b1i, plus a2 plus b2i, and we want to add these together and take the conjugate. We want to show that this is the same as the conjugate of z1 plus the conjugate of z2. So, well, the real part is a1 plus a2 plus b1 plus b2i. We're just combining like terms. And we're going to take the conjugate of this, which means change this sign now. So a1 plus a2 minus b1 plus b2i. Okay, now let's regroup this into the a1 with the b1 and the a2 with the b2. Let's rewrite this as sort of like the original complex numbers. So this is equivalent to a1 minus b1i plus a2 minus b2i, which is z1 conjugate plus z2 conjugate. So that's what these are doing for us. These summarize what we can do with conjugates, and these can be useful to us. So we've looked at addition, subtraction, multiplication of complex numbers, but what about division? Well, let's take a look here. We've got 5 plus 5i divided by 1 plus 2i. And we want to end up with another complex number, so something plus something I. That should make sense. When we multiply, we get a new complex number. When we add two complexes together, we get a new complex number. When we divide, we should get a new complex number also. So this is sort of like rationalizing the denominator with radicals. We don't want an I in the denominator. We only want a single I in this problem. So what do? Well, we saw some properties of conjugates, and we want the denominator to be a nice, regular, ordinary, non-imaginary part number. We only want a real number in the denominator. So what we can do is we can multiply the denominator by its complex conjugate. And if we do it to the denominator, we also must do it to the numerator. So we're effectively multiplying by 1. We have something divided by itself. And now we expand, and we saw that when we take a complex number and multiply by the conjugate, we could expand this, we could FOIL, we could notice that this is a difference of squares. We also saw on the previous slide that when we take a number times its conjugate, it's the same as the magnitude of that number squared. So we'll do this two ways in the denominator. Let's FOIL first. 1 minus 2i plus 2i minus 4i squared. And that's going to be 1. These will become 0 plus 4, because I squared is negative 1. So this is 5. The denominator is 5. Now, it also said that it's the magnitude of this thing. It's the magnitude of this thing squared. So what's the magnitude of our z1? Well, it would be the square root of 1 squared plus 2 squared, quantity squared, or guess what, guys? It's 5. Another way to look at this is the difference of squares factorization. It's going to be 1 first thing squared, a squared minus b squared, so minus 2i squared. A lot of different ways to look at how to expand that denominator. But all of them give us a non-imaginary number in the denominator. This is just over 5. Now in the numerator, there's no quick trick here. We're not taking a complex number times its conjugate anymore. It's just two complex numbers multiplied. So we have to expand. 5 minus 10i plus 5i minus 10i squared. Remember, minus 10i squared becomes plus 10, so we have 15 plus minus 5i, and now we can split this into a real part and an imaginary part. 15 over 5 minus 5 over 5i, and will those fractions reduce? We have 3 minus I. So z1 divided by z2 is 3 minus I. Okay, let's beef it up. More division. We want to find z. Z is a complex number, where if I take that complex number plus 1, I divide it by 3 plus I, that's going to be equal to the complex number minus 5i equals 2i minus 1. Now, in some problems, I take the z and I write it as a plus bi. Here I'm not going to do that because I have this z more than one place. Before I think of it as a plus bi, it might be helpful if I could get all of my z's in one spot. That's sort of an equation solving strategy that we've used throughout the years. So let's get rid of these fractions. Let's cross multiply. So we have z plus 1 times 2i minus 1 equals 3 plus I times z minus 5i. And z is just a number. It happens to be complex, but it's a number. We can FOIL, we can expand these out the same way we do with regular real numbers. So we have z times 2i minus z minus z plus 2i minus 1 equals 3z. We've got minus 15i plus I times z minus 5i squared. Oh, that's nice. Minus 5i squared. That becomes plus 5. So now we got to get all of our z's to one side. I'm going to move them to the left. Z times 2i minus z minus 3z minus I times z. And I'll move everything that doesn't have a z to the right-hand side. So negative 2i plus 1 minus 15i plus 5. Remember, this part became plus 5. I forgot an I. So now these four terms on the left all have z in them. We have 2i minus 1 minus 3 minus I equals, let's combine like terms on the right also. We have 5 minus 17i, 6 minus 17i. And on the left side, there are some like terms to combine. We have z times, what do we have here for the real part? We have negative 4. And then we have plus 1i. Okay, so how do I get this z alone, this mystery complex number? What do I do? Well, we have a complex number times a coefficient that happens to be complex equals another number. How do we solve a mystery thing times a number equals something? We divide. We're going to divide both sides by negative 4 plus I. So z, our mystery complex number, is 6 minus 17i over negative 4 plus I. But we don't leave our answer like this. We need to actually do the division. So in this case, that means we multiply by the complex conjugate of the denominator, which is negative 4 minus I and what we end up with in the numerator is negative 24 plus 68I minus 6I, and then it would be plus 17I squared, but I squared is negative 1, so this last term up there is minus 17. In the denominator, we have 16 minus I squared. Minus I squared is the same thing as minus negative 1, so plus 1. So our mystery complex number z, combining like terms, we get negative 41 plus 62, I in the numerator, and they are both over 17. There is my z.